Associate Director at the Human Engineering Research Labs, where our mission is to improve the lives of people with disabilities through advances in technology and services, largely in the healthcare sector. But this is an example of where we're really helping to develop more rigorous standards in sort of infrastructure. I'm also a co-founder, advisor, and a part owner of pathVu. And this work was sponsored largely within the university through federal grants and foundation-sponsored research sources. And it's in excess of $2 million. And I'll show you that this has been a work by a large number of people over more than a decade. The motivation was really about the incidence of neck and back pain for wheelchair users. And so we, based on clinical work back in the 90s, recognized that wheelchair users reported much higher levels of neck and back pain compared to the rest of the population. And we started asking the question about why. And one of the areas where this work had been developed very systematically and thoroughly is in the occupational hazards literature. And they developed a testing approach as well as exposure thresholds for vibrations. And this was developed largely around for people that were heavy equipment operators, bus drivers, semi-tractor trailer drivers that were reporting back and neck pain. And what they determined was, depending on a certain amount of time of exposure, you could be at risk for health consequences. And so what I show on the bottom left are those vibration standards. The left lower quadrant is a safe zone. The upper right quadrant is the unsafe zone. Along the x-axis is the time of exposure, and the y-axis is the RMS vibration exposure. And so we use this as the starting point for our research. And our first question was, really, do wheelchair users, when they're using their chairs, are they exposed to unsafe levels of vibration? So are the exposures that they see day to day in that upper right-hand quadrant? And if so, what are the risk factors? What are the driving forces behind that high level of exposure? And what are, how do we reduce that risk if we find out that it is a problem? So we've done this work. The first publication was in '94. So we've been working on this problem for a very long time, over a decade. The papers and standard highlight all the stuff in red is stuff that I have participated in. So this is the work of many dozens of people. So I want to recognize all of them in the process. And early on, what we wanted to do, again, answering that first question, is measure vibration exposure out in the community. So we developed some data loggers. We instrumented wheelchairs and that were used in the community by wheelchair users, and we just measured that vibration. And what we found was that the answer to the question is yes. The vast majority of people using wheelchairs, this is true for both manual and power, fall in this upper right quadrant, with 70% looking at the seat base of the wheelchair. If we're looking at those vibrations, which are the most risky for anybody in a seated position, 70% were in that above red zone, and about 30% fell into what we consider a yellow zone, which is a hazard zone or a health caution zone, but not a tremendously high risk. And so the answer to the primary question was, yes, that there is a potential health risk. And then we asked the question, what are the risk factors? And what are they within the wheelchair themselves? And then also, what are the risk factors related to the environment? For the wheelchairs, we looked at several different aspects of the wheelchairs. I'm sort of highlighting two. One is the cushion, which most wheelchair users sit on for pressure relief, but there was also a hypothesis that there was dampening going on with that cushion. And what we found was that actually, for the frequencies we're trying to dampen, the cushion does no good and in some cases makes things worse. The only exception were cushions that were flotation cushions that used air, and so there was really no prevention or risk reduction overall with cushions, because a wide range of cushions are prescribed, and they focus on prescribing a cushion based on pressure relief and not vibration dampening. We also looked at wheelchair suspension, which is available on some manual wheelchairs, but on most power wheelchairs, and found that there are some benefits for the what we call the high frequency, low amplitude vibrations when you put suspension on the front wheels, but overall the suspension itself did not mitigate the health risks from vibration exposure. We then started focusing on the environment and had pavers installed in our outside of our lab, and had people propel or drive wheelchairs over the different pavers and concrete sidewalk systems, and looked at the vibration exposure over each of those, and found that the vibration exposure depended on the bevel of the paver and also the pattern, and some pavers resulted in less vibration exposure than poured concrete, and I'll show some of that data here. And the way I'm describing this is from a paper we published in 2005, is the numbers in the table are demonstrate how many hours somebody in a wheelchair could drive over those different surfaces safely. So higher numbers are better. So the first row here is poured concrete, and that shows the number of hours over these different, for the first column is a manual wheelchair, the second two columns are electric powered wheelchairs, so power wheelchair users. And what we found is, and each of these boxes represent paver designs and bevels that are actually, based on the vibration exposure, less risky to travel over. And so that was an important finding for us, largely because there have been, and this was filtered through the access board, complaints and concerns about paver surfaces on sidewalks relative to poured concrete. And so this, back in 2005, was the first evidence that there wasn't a universal truth related to pavers versus poured concrete. It really had a lot to do with the bevels themselves and how the pavers were laid out. And so based on that research, we received funding from the U.S. Access Board to develop a roughness standard. And this was, the reason for the funding support here was twofold. One is that we had done many years of research to demonstrate that vibration could in fact be a health risk to wheelchair users. And the other piece was, and the way that the priorities of the Access Board have to do with complaints of people with disabilities. And so the U.S. Access Board was receiving a lot of complaints and concerns related to sidewalks. We had demonstrated in the lab and in the community that the vibration may be the consequence of the discomfort and health risks. And so we received funding to establish a roughness standard that then could be used by the Access Board to promote safer sidewalks for wheelchair users. And so I'll pass this on to John Duvall, who's going to talk about the development of the roughness standard. He did this as his master's thesis. And then Eric will pick up and talk about the tool that was developed as part of the study and is now licensed by pathVu. So thanks, John. It's all yours.
Thanks, John. And yeah, I'll kind of pick up where he left off with discussing how my research project fit into this. So first, we had several project goals, but the first thing that we did was do a literature review on roughness measurement and analysis techniques, primarily used in roadway and other areas in the scientific community, to see if there was already measurement tools and analysis techniques that could be useful for sidewalks. After that, we did a study where we wanted to characterize the relationship between the roughness of the surface, which is kind of the general way of describing roughness is it's the sum of vertical deviations over a horizontal distance. And we wanted to see how well that correlated with the vibration exposure and how well it correlated with user responses in terms of rating different sidewalks. So based on that research, then we wanted to develop thresholds which would correlate with the vibration exposure and time durations that John mentioned earlier. Then we obviously wanted to design a measurement device so that surfaces could be measured to know how they would cause vibrations to wheelchair users who would be driving over them, and then promote the thresholds and measurement techniques and everything through publications and standards. So how we started doing that after we did the literature review and found that there were no real measurement tools or analysis techniques that seem to apply well to sidewalks, because sidewalks compared to roadways have many more joints, which is transitions from one surface to another. So all the gaps between bricks or between different segments of concrete on concrete sidewalks cause it to be quite a bit different than roadways. So we set up this runway here that had a sequence of different widths of boards. So we could basically change the frequency of gaps between the boards and also change the width of the gaps between the boards. So here's kind of a description of 9 different surfaces that show how we were able to adjust the roughness index of different surfaces when we had wheelchair users driving over them. And we also had them drive over different community surfaces. So these aren't surfaces that we actually had them drive over, but this is just kind of a, I think, a good overview of what types of surfaces are actually out in the community and why this research was necessary, because you can see there's all kinds of different surfaces in the community, and all of them can cause different amounts of vibration. So we really wanted to be able to have a tool or some way of saying, you know, this surface is going to cause a lot of vibrations to wheelchair users versus another surface that might not. So again, when we did the study, we had accelerometers placed on their chairs and had them drive over the 16-foot section of our simulated surfaces, and also several surfaces around our location wherever we were doing the study that we found that had different types of surfaces, so brick and concrete, potentially cobblestone. We tried to find as many different variety of surfaces as we could. And then we also had them rate the surfaces in 2 ways. One was just whether they felt the surface should be acceptable or not, and then also rating it from 0 to 5 based on the rater form that you see there on the bottom right. So another thing that went into how we determined our roughness calculation and why we felt that most of the things in the roadway analysis techniques weren't applicable to sidewalks is that we realized that just purely looking at the sidewalk and figuring out all the vertical deviations over the horizontal distance could not really tell the whole story in terms of how the wheelchair would experience the vibrations. So if you see on the bottom left there, what we realized kind of early on was it didn't really matter how deep a crack was. If it was pretty narrow, the wheel wouldn't be able to drop completely down into the crack. So it really had more to do with kind of the width of a crack as opposed to the depth of the crack. So we developed what we call a wheel path algorithm that was used to kind of filter the profile of the surface to show how a wheel would actually travel over the surface. And what you see on the right there is kind of a plot of how we did the wheel path algorithm over one of our simulated surfaces. So you can see essentially it was every 4 inches, but you can see the red line drops down a lot farther than the black line. And the black line is kind of how the wheel would actually travel over that surface. And so again, we were basing all of our data that we were getting to the ISO standard for vibration. So this is just kind of another review that it depends on the amount of vibrations, the RMS vibrations, but also the duration of exposure. And so this is kind of a graph of our results of what we found, that the roughness of a surface and the vibrations that wheelchair users were exposed to correlated fairly well. So we started looking at what magnitude of roughness correlated with the caution zones of the ISO standard. So this is kind of showing how we determined those numbers. And on the top, you can see we're based on the vibration exposure, and the lower one there is based on the survey results. And these are all kind of what we envisioned as possible thresholds based on the data. So we tried to find something that was kind of in the middle, or kind of made sense to what we thought thresholds should be. So if you look at the survey results, you can see that the percent acceptable there is basically saying that 75% of our research subjects said that surfaces above that roughness would be acceptable. And then the 50% is 50% of the research subjects said surfaces above that roughness would be acceptable. And then also for the good and fair of the rating. And so based on this, we kind of determined that we thought 0.6 inches per foot and 1.2 inches per foot would kind of fit pretty well with the health caution zones, based on how long it made sense for people to be traveling over sidewalks. Obviously, you know, wheelchair users wouldn't typically travel over a sidewalk 8 hours a day. But we felt anywhere from 30 minutes to 2 hours could potentially be applicable, depending on if they were living in cities and commuting on sidewalks to and from work or other places. But we also realized that even though they might not be on sidewalks that long, they also are exposed to vibrations in buildings and in vehicles and stuff. So we wanted to make sure that they weren't exposed to high levels of vibrations just on the sidewalks, and then also vibrations other places that could lead to health risks throughout the day. So based on our numbers of the surfaces these are pictures of surfaces that we did test, and these 4 surfaces all were below our lower limit, meaning that these surfaces would all be safe for wheelchair users to travel on without being at risk for high levels of vibration exposure. And one thing to point out here is you can see there's poured concrete, there's also stamped concrete down in the bottom right, and there's also a brick surface in the top left that shows different surface and different characteristics can result in low levels of vibrations. These surfaces were all in the caution zone, so these surfaces all had a roughness number between 0.6 inches per foot and 1.2 inches per foot. And you can see, again, there's all different variety of surfaces. And one thing to point out here, what we've kind of noticed is that these surfaces, compared to these first 4 seem to be all pretty new surfaces, or at least in good condition. These next 6 surfaces all seem to have a little bit of wear, that you know, they're probably older, been through a lot of hot and cold temperatures, and have started to get a little bit warped. And then the last surfaces here are what were above the health guidance caution zone numbers that we determined. These ones you can see have a lot of patchwork and that are very, very rough. You can tell just by the pictures. So based on all of this research, we helped to draft this standard, which is basically just a description of how to measure the roughness of a sidewalk using whatever tool you could use that would fit the criteria to measure the sidewalk. And then this essentially just shows taking a profile of the sidewalk, how you do the wheel path algorithm that I talked about, and how you can determine what the roughness of a surface is. And so here's just a few of the fine details from the standard. What we basically say is speed should not affect the data, no matter how you're collecting the data. it doesn't matter how fast you collect it. The interval measurements we prescribed as being this low because mostly because of industry standards of how to install bricks and differences that the gaps are typically between 3 and 5 millimeters. And if you start measuring the profile at somewhere around 5 millimeters or so, you actually could miss some of the gaps. So we wanted to make sure that it was low enough that you could actually make sure that all of the gaps between all the joints were measured. And then we also have kind of a precision of how to round data based on whether you're measuring in millimeters per meter or inches per foot. And then there's also a paper that should be publicly available. I think we might have a link towards the end of the slide or this link that kind of shows why we, like I showed earlier, why we proposed the thresholds that we did, which are 50 and 100 millimeters per meter or 0.6 and 1.2 inches per foot. So that hopefully that gives kind of a good background of how we went through the study, how we came to our conclusions, and how those conclusions are going to lead to changes throughout the pedestrian pathway infrastructure. So, Eric, I'll pass it back to you.
Thank you, John. And a note on the publication that John talked about. The publication may be publicly accessible in about a month or so. So we will keep you updated when that AT journal is public. Based off of all of this research, we saw the need to develop a tool to be able to measure what roughness is based on the standard. So we've done there's been a lot of evolution and iterations through the development of our pathMet device. And if you'd like to learn a little bit more about our pathMet device, you can go to that link there, pathVu.com/pathMet. But this tool was designed specifically to measure the standard and look at roughness of sidewalks and pathways. And some of the other items that it collects, in addition to the WPRI roughness, are things like lippage or tripping hazards along sidewalks, running slope, cross slope depressions, in addition, the location and images every 10 feet. So this device collects this data continuously at a millimeter resolution as it's propelled over the surface. Then we take that and we analyze the data to come up with these numbers and calculations. After that, we then display it on any GIS platform such as ArcGIS, and I'll show you some of that data shortly. And the pathMet device, as I mentioned, it collects the data continuously. A lot of typical data collection methods currently collect the data using a tape measure or a level, and it's more, it collects at specific spots. The nice thing about this is it collects every piece of information along that route that we collect. So you don't have to piece that data together itself. It's continuous. So pathVu as a whole, we focus on sidewalk and pedestrian pathway data and mapping. So the very first level of data that we collect are these sidewalk map center lines. So this is a map of some of the locations in Pittsburgh and the sidewalk locations. So this is the very basic piece of information that we collect. But then we have our tools to collect additional data. So I mentioned the pathMet device, which is that high-resolution tool that we use. But we also saw the need to crowdsource data from pedestrians as they're going along the route. So a user can download our pathVu app on either Google Play or the App Store and report the location of different attributes along the route. And these different attributes could be a tripping hazard, it could be a curb ramp location, it could be a rough patch of sidewalk. So then we start to collect this information from where people think that there are problems and then we can take our pathMet device there and collect that data. And this is an image of our pathMet visualization. It shows a green, yellow, red heat map of the route that we've collected for a project in downtown Pittsburgh. And so this data is according to the ADA, the Americans with Disabilities Act, guidelines. And so if one of the characteristics, roughness or slope or tripping hazards, is in that caution zone, it becomes yellow. And if one of them is in the red, in the danger zone, it's turned red. So we collect this data, and then we can help display this data, help organizations and companies visualize it and prioritize improvements to the infrastructure. And what you can actually do is, if you are interested in looking at it further, you can go to our website, and then on the main page there, you can actually interact with the data, click on some of the segments, and see the type of information that is collected. And it'll show you the roughness of those locations as well. So we have our pathMet visualization that I showed, and then this is one example of our pathVu app data visualization. It shows a heat map of the hotspots in a Pittsburgh neighborhood of where people have reported data. So obviously the hotter spots are where there have been more reports. And then if you were to zoom in on the data, you could actually click on individual locations, individual icons, and see the type of item that was reported, you know, when it was reported, the image that was included, and other details about the data that has been reported. So together, the data looks a little bit like this. Again, you see the underlying heat map of the pathMet data. If you click on one of the lines, you can see additional data. In this case, you can see that the roughness is above 100 millimeters per meter, above that recommended threshold. And it looks like an aggregate surface of some sort that has caused the roughness to increase in number. And then you also see other icons on the map, such as wheelchair symbols that indicate the location of a curb ramp. You see triangles that represent other types of hazards along the route. And then in addition, there are other circles and dots around these areas that show the additional pathVu app data. They could be other curb ramps, other tripping hazards, etc. So in the future, what some of these, this research and this standard means is, first, in 2017, the Access Board, who governs the ADA, is coming out with their Public Rights of Way Accessibility Guidelines, or PROWAG. So the PROWAG will discuss the Access Board's suggested guidelines and thresholds for what is accessible for pedestrian pathways. And one of the things that it will discuss is roughness. It will talk about it in the preamble about the importance of roughness and limiting roughness to ensure safe routes for people with disabilities, especially for wheelchair users. So roughness will be mentioned in these coming guidelines. Then it will be up to the DOT and DOJ to enforce enforce this roughness standard and the implementation of it, including possibly our suggested thresholds for what's for the levels of acceptability. And so pathMet, as I mentioned, is a tool that can be measured, be used to measure the standard, and was used to develop the standard. It can also help to understand how different surfaces compare to one another, and start to understand maybe what types of surfaces can be and should be installed. And then also, how do surfaces evolve over time? How do, you know, if you live in Pittsburgh, we have a lot of cold weather, ice, snow. How do the surfaces change over a year or 5 years of cold weather? So we can start to understand those type of characteristics about the surfaces as well. So I'd like to just quickly recognize some of our partners and supporters. especially the Access Board, who funded the development of the research, ICPI, the Interlocking Concrete Pavement Institute, and the Brick Industry Association, who funded the development of the pathMet device, and then also the University of Pittsburgh, whom we are a spin out of and licensed the pathMet technology from. And so finally, I just want to show some publications and standards that relate to this Sidewalk roughness standard. If you'd like at some point, these slides will be available online. This video and webinar will be available, so you can click those locations and view the data if you like. Finally, I'd like to thank all of you for attending. I'd like to thank Dr. Perlman and John Duvall for presenting and participating in the webinar. And at this point, I'd like to open it up for Q&A.